Hi, this video gives you a quick overview of the Beer's law and its simple application in single analyte analysis. Beer's law is defined as the amount of monochromatic radiation absorbed by the sample. It is a powerful technique for analysis of sample in chemistry lab. Sometimes you are dealing with unknown concentration of sample in chemistry experiment. In this example here, 5 sample solution with varying concentration from 0.02 molar to 0.1 molar. So you can see that as the concentration increases from left to right, the intensity of blue color also increases correspondingly. So low concentration shows light blue color, while for the high concentration, a deep blue color. It is not uncommon to run the solution in the lab that we do not know the concentration of. For example, here on the right, this is the solution of same sample that we don't know the concentration or molarity. We can estimate the unknown concentration based on the intensity of blue color in that solution. When we look carefully, we can see that the color is darker than 0.08 molar but lighter than 0.1 molar, so that the molarity can fall between these two regions. However, we need more accuracy to obtain the exact concentration, and this is how a Beer's law can be applied. Now, let's explain the relationship between absorbance and Beer's law. Here, A is for absorbance. Epsilon represents the molar absorptivity, a measure of how well a chemical species absorbs a given wavelength of light. B represents the path length, or the distance light has to travel through the sample, which is relevant because the more of a substance the light travels through, the more that will be absorbed. And C is the concentration of the sample, which again is relevant because the more concentrated, the more absorbance that will occur. Absorbance is measured by comparing the intensity of the beam of light as it enters the sample cell and the intensity as it leaves the sample and strikes the detector, which are P0 and P respectively. According to Beer's law, absorbance is directly proportional to the cell path length, or B, and concentration of the absorbing species, or C. So let's see the application of Beer's law in a single analyte analysis using UV and visible spectrophotometer. We go back to the 5 sample solutions with varying concentration from 0.02 molar to 0.1 molar and an unknown sample. To determine the concentration of unknown sample, Beer's law can be applied. Those samples have been analyzed using UV and visible spectrophotometer to measure the absorbance at maximum wavelength of 670 nanometer in the visible region, and the results has been listed in this table. As you can see, as the concentration increases, the absorbance also increases. And this is in line with what Beer's law has said. This data can be used to create Beer's law plot and absorbance versus concentration plot. Once I have this plot, concentration of unknown can be obtained by using the trendline equation. But we need to recognize what is the variables are. In this case, Y is absorbance and X is concentration value in terms of molarity. For the unknown solution, we know that the absorbance is 0.85. So by substituting 0.85 for Y, and we can solve the X. So the concentration of unknown is 0.092 molar. Let's try one calculation example to put this into context. The question is, a 7.25 10 power of negative 5 molar solution has an absorbance of 0.356 when measured in a 2.1 cm cell at a wavelength of 5 to 5 nanometer. Calculate the molar absorptivity for that solution. So by using Beer's law equation, we just substitute absorbance, concentration of analyte, and cell path length from the question to the Beer's equation, and then we can get the molar absorptivity. So the answer is molar absorptivity is 2.34 times 10 power of 3. For activity, please try to answer this question. You can refer to the previous example to guide you to the answer, and the answer will be given after this. So for the solution for this activity, just substitute all the given informations from the question to the Beer's equation. Then you can get concentration of analyte is equal to 0.064 molar. So this is the answer for this activity. That's all for this video. Thanks for watching.